Good afternoon and welcome to another one of our Wednesday afternoon practical sessions on doing stuff for your PhD. And again, we've got Professor Richard Hift, who's going to be talking to us about the data again. As you know, and as you can see on the UKZN YouTube site, there are several of his talks on what to do with your data, how to anticipate the data, what to do with it, how to collect it, etc. I'm going to hand over to you, Richard. Thanks again for the talk.
Thank you, Colleen, and welcome everybody. Let's go straight to share the presentation. Right. Interpreting and analyzing data is a little bit difficult to present. The main reason being that it is so utterly dependent on what you're doing and what sort of results you have. So there's no way anybody can give you a sort of standard boilerplate template of how to analyze your results. It is a critical skill which you need to pick up, and like any other skill means spending time and a lot of thought and intellectual effort on it. And to start off with this point, you know, the famous poet Alexander Pope, who said, "Fools rush in where angels fear to tread." And in this context, what I see it as meaning is you can't just rush in and interpret data if you don't understand what it is that you've actually done. You need to understand the methodology. You need to understand the limitations of the methodology, so that you don't go making interpretations of things that your method itself is not robust or good enough to support. But above all, you actually have to understand what it is that you've actually done. This may sound self-evident, but again, speaking from experience, particularly at master's level, but not infrequently at PhD level, I've helped people who've come with data. And in speaking to them, it's become quite clear to me that they don't actually know what they've done. They can point to a row of numbers, but they don't really seem to know what role that row of numbers is meant to play in terms of proving their thesis or answering their research question. It's just a lot of numbers, and somebody must help them decide what to say about it. So I can't stress that enough. And of course, the corollary to that is it's actually a very sad event that people can get to the end of data collection, have results, and still at that stage not understand what it is that they're attempting to do and what those numbers mean. So please make absolutely certain at an early stage of your project that you fully understand what it is that you're doing. This is particularly so if your project was given to you by somebody else. You know, your supervisor said, "I need somebody to do this project now, run with it." Not infrequently under those circumstances, the candidate has just got in the habit of doing what they were told and therefore doesn't actually understand what it is that they've done or where it fits in. You cannot interpret data if you don't even understand what they are meant to mean. Right, a slide that I've shown before, my personal belief, collecting data is only about 10% of the learning of the PhD. The other 90% is made up in more or less equal parts of the learning you did before you handed in your protocol. That's where you really got to grips with the whole concept of research question, hypothesis, aims, objectives, methodology, the scientific method, etc., which is a huge learning curve, which is why so many students feel, so inadequate and uncomfortable in the early stages of their PhD. Another 30% is in the analysis. It's not just the how-to of the analysis. It's actually getting in the habit of thinking critically during the analysis. What else can I find in this data? What are the strengths of this data? What are the surprises hidden in this data? What doesn't make sense in this data? There's a huge amount of learning there. And then the other 30% is what you learn as you write everything up. Again, not just the technical stuff like how to reference, but again, how to marshal an argument, how to lay out an argument clearly and logically, how to avoid error, how to protect yourself against inevitable criticism in advance before it even happens. So there you have it. Don't rush into data collection. That's actually only 10% of the learning of the project. Everything else, including today's topic, is a 30% each. So just a little bit of time on interpreting data. It all begins with data presentation. Now, I talked about this last week, so I'm not going to go into it again. But it absolutely begins, if we are talking about numeric data, not qualitative data, with an absolutely clear, meticulously laid out spreadsheets, with everything in the right place, in the right format, and absolutely no errors. A single error in a single cell discovered after your statistical calculations means that you have to throw away those calculations, correct the error, and then run all the calculations again. And it's not infrequent that we actually end up doing that over and over and over again because we keep picking up little errors. Something doesn't make sense. Why is this value so low? And then we go back and look and see that a naught crept in somewhere in the column of numbers and hadn't been noted, or a result was left out, or two rows were mixed up. So check your data to the best of your ability. As I said last week, you will be working with your spreadsheets during the analysis, but be extremely careful. Excel has a horrible habit of completely muddling up your data. And it's not really Excel's fault, it's what we do with it. But it's very, very easy to missort things so that columns end up with different cells referring to different rows and not to the rows they're meant to. As I said last week, always keep backups that you don't touch, so that if you do irretrievably mess up a spreadsheet during the analysis, you can at least go back to something that you know really is correct. Right, so meticulous layout of your data, a sort of just a few columns here, but you've got the idea, everything extremely neat, everything consistent, everything in a single column with a variable name at the top and nothing else written there, and so on and so on. Right, so the presentation of your data to yourself, to statisticians, etc., is absolutely critical. Thereafter, it's a matter of argument, discussion, reflection, further reading, trial and error, and that goes on and on and on. Now, you may be lucky, this may be what you might call a somewhat simple experiment. You may have done this to 5 mice and that to 5 mice, and you've got 10 numbers as a result. Or perhaps that doesn't quite apply here. But particularly in the messier stuff, medical stuff, clinical stuff, sociological and educational stuff, there's often a large amount of data and numerous possibilities included in that data, not just what you think you set out to do. And often there are different ways of pulling the data out that actually mean different things. So it needs a large amount of, as I said, argument, discussion, reflection, further reading, trial and error, in order to come down to what you believe is the very best interpretation of your data. A problem that often occurs, again in my experience, is people just wade into their data, do the obvious, which may not even be the correct obvious, maybe the incorrect obvious, and think the job is finished. There's absolutely no point in doing research if the conclusions at the end are invalid, because you are not curious enough, reflective enough, or self-critical enough to actually extract the right interpretation from that data. Not infrequently in my experience, as one goes through it, one gets new ideas, one might have to learn a new technique. I'm working with a PhD student called Mayuri Govind, and we went through a whole lot of educational stuff. And then we realized that the best way to handle it would be with a relatively new form of educational assessment. I'll think of the name in a second, which actually required us to learn a whole new field of what's called psychometrics, assessing the quality of a test, the reproducibility of a test, its validity, and so on. And we had to go through a whole learning curve with Stata to learn how to perform those calculations on Stata. But the end result was a very much stronger interpretation and analysis than what we first set out to do. So don't fall into the trap of thinking that once you've got your data, that's it, and it's just a quick matter of analyzing, and then you can start writing. If your data are rich, it often takes a lot of work and a lot of extra effort and a lot of thinking to extract the full richness out of that data, and not just some sort of superficial interpretation. And that's why I've really said the reiteration, you go through it over and over and over, letting the data talk to you. And each time you have a look, you suddenly think, you know, I compared the males with the females. I wonder if it would be different if I did it the other way around. You know, let me compare the kidneys with the livers and see what that tells me. That is another very, very common thing I find. There may be 10 or 15 possible ways of analyzing data statistically. People have only done 1 or 2. And when you do 3, 4, 5 through to 15, suddenly new insights arise. And it can make all the difference between a really startling, interesting set of conclusions and a very boring, dull set of conclusions, which may in the end come down to publishable or not publishable. Right. Keep your statistician on a tight leash. This is something I've often noticed. Your statisticians sometimes have a biomedical background, very often not. They're very clever people with degrees in applied mathematics and statistics. They know all about statistics, but very little possibly about your biological field, your psychiatry or your gynecology, you know, or whatever it may be. And so they do have a tendency sometimes to run with the right test on the wrong data or the wrong test on the right data, not because they're not good statisticians, but because they didn't actually understand the principle of what made sense in the comparison. For example, to use a trivial example, they might not know that it makes no sense to compare livers with kidneys. They're far too different. As far as the statistician is concerned, they're both organs. Why can't we compare them? But you will know that a liver can't be compared with a kidney, but males can be compared with females. So you really have to understand the questions you're asking to guide the statistician in the right direction. It's not a case of dumping data on them. So often now I've had people come and see me who've been to the statistician and came back with a set of instructions which they don't understand themselves, and therefore they don't know how to proceed. And sometimes when I look at those instructions, I see where the statistician is going, and other times I suspect that the statistician, in fact, was not fed the right information as to what was required of them, and it's therefore just done something, but it's not the most helpful thing. It's like handing your car in because the steering is loose, but not actually telling the mechanic. So it comes back with a new exhaust instead. It doesn't help. Hence the old saying there, GIGO, garbage in, garbage out. If you don't feed good stuff to your statistician, then you're not going to get good stuff out. And I can't stress enough the importance of developing some comfort with statistics yourself. You don't have to be an excellent statistician, but you do have to understand the basic principles. Otherwise, you cannot guide your statistician. All right, then just a few points. These are also common errors. Don't ignore data. often I'll see some very interesting data on a page, but it just hasn't been used. Okay, so I have to say, but you've got a column here for your renal function. Why haven't you used it? No, I decided it wasn't relevant to my project. So I insist that we have a look at the renal function, and lo and behold, a really interesting insight arises that suddenly renal function is the thing that correlates with whatever you were doing, and not the liver function that you thought you were actually studying. Just because you set out to study one thing like liver function does not mean that you cannot develop new insights along the way, come across surprising results, take those on board and run with those instead. So make sure you really have looked at all your data and don't just ignore areas of data. A sad one, don't contradict data. Okay, this is also not uncommon. I have to say it really is a sign of scientific immaturity. These are people who come to the analysis already knowing what the answer is meant to be. It's what they were told it would be, or what they think the existing literature says. So the data says 2 and 2, and so they analyze, say their conclusion is 3. And I say, but hang on, 2 and 2 makes 4, not 3. I know, but everybody knows the right answer is 3. You can't do that, okay? You cannot contradict your data. So don't say the data told me that men are taller than women, but I'm still going to say that women are taller than men. Don't overlook data, as I mentioned. This might sound a little poetic, but listen when the data try to tell you something. Again, this is something I've seen so often. Okay, there are interesting things hidden in the data beyond just the straightforward things that you collected, knowing you were going to use them. And I've had several examples in working with students here. This was a project by other people that they could not get published. They had a database of many, many patients with inflammatory bowel disease and just wrote up a standard report on the database whether there was an increase in cancer. Not very exciting. The answer was there wasn't. And so it just got bounced from journal to journal to journal. And eventually I was asked if I would please just help out this particular candidate. I had to look at the data, and immediately something else did jump out. Yes, there was no increase in cancer in this group, but there was a lot of skin cancer. And the skin cancer was only in the white patients who had taken this particular drug and in nobody else. So we got the paper written up in a very reputable journal showing an increased risk of skin cancer in an at-risk population. It then got published, and that's because I spotted an interesting angle in this data, which was not the one that people had set out to see. Right. Then these things, of course, all come under the heading of fraud. Don't force your data to give you the answer you want. Under no circumstances, alter data or change it. I've put ignore data here, but this time I mean deliberately ignore data, overlook data, leave it out of the analysis because it doesn't tell you what you want to see. Extremely dangerous. And don't massage data, which is a sort of combination of all of those to just slant the data so they come very nicely and give you the result you want. The classic places is when your P equals 0.06, but you find if you just leave 2 data points out, then it becomes P equals 0.05. Now you can only do things like that if you can mount an absolutely defensible reason as to why it was appropriate to leave those particular points out. For instance, they were taken after the study finished, or there's a strong reason to believe that the machine had not been calibrated that day, but it can't be made up. It's got to be genuine. And what most journals will want, if you are honest, is when you do things like that, you state it in the text. 2 data points were removed because. Don't just quietly do it under the table. Anything you do to your data that materially affects the outcome should be recorded in the paper. Otherwise, you really can be accused of scientific fraud. Right. And then, as I said earlier, so much of the learning comes from asking other people about your results, discussing your results, arguing about your results with your supervisor, your fellow students, revisiting your results and looking at them again. As you write your discussion, go back and think again about the results. And I suppose I should have put the word present here too. You know, present those results publicly to other people. Let them comment. Often very interesting insights will occur. Things like, did you think to compare the liver with the kidney? Or are you quite sure that's the right statistical test? Wouldn't something else be better? It may not just be a case of right and wrong test. There are many cases in which both tests are acceptable, but one actually provides more insight than another. Classic example that both Colin and I have used recently, you may have presented your results as age groups 20 to 30, 30 to 40, 40 to 50. But in fact, you have got the original numbers, 20, 21, 23, 24. And you could throw out the 20 to 30, 30 to 40, and go back and do a proper regression and correlation on the original data. But it might be in discussing and presenting that somebody suggests that to you. Right. I'm going to go in a little bit. This is more about writing a paper, but I'm going to approach this from a slightly different angle. We're not going to learn statistics today, but we are just going to remind everybody, place in context, what sort of methods you should be applying to what sort of situation. Right. Okay. Firstly, you must understand which statistics package is being used, and that must be reported. You're all going to write a statement like this in your paper. An alpha level of 0.05 was considered significant. You absolutely have to understand what that actually means. What does people's 0.05 mean? And what does significance mean? And what can make a thing look significant when in fact there is no real effect? And what can give a thing a non-significant p-value even when there is a real effect? I find those two things are often left out and not understood. The difference between non-significant, implying no real difference, and non-significance, implying sample size too small. Completely different importance. Right. Important to understand how to set out your results and how to describe them. It's called a central tendency. That's whether you're going to use a mean or a median, and a distribution. Okay. In general, it's fairly simple. If your data are normally distributed, so you do need to understand what that term means, report it as a mean and standard deviation. Otherwise, so we have it there. Otherwise, as results are reported as median and the interquartile range, which I'm not going to explain or define now. If you don't understand it, it's just a good pointer that you really do need to spend some time on that for skew data. But again, a little bit of knowledge is dangerous. And it's as well to know that it is not totally wrong or forbidden to use means, standard deviations, and parametric tests for skew data under certain circumstances, such as large data sets. So you really do need to understand how the data should be set out. Right. Right, pretty better. Okay. In analyzing your data, I find two things absolutely invaluable. One is making tables. So as I analyze my data, I make tables and I write down my results. You know, so having gone through and got all my means and standard deviations, I set them out in a table. I often end up with 8, 9, or 10 tables, of which only 2 will survive to go into the eventual paper. But it's in looking at those tables, which really are a summary of the findings of my analysis, statistical analysis of my results, that the meaning starts to become clear. So make tables of results and use copious graphs and figures. That often is so useful at demonstrating what's really going on. So again, it's a case, all of this is telling you, dig deep into your data, get to grips with it, speak to it, let it speak to you, understand it. Don't just ask somebody to print out some numbers that you can write up in your paper. You do need to understand what's actually going on. So I found graphs and tables very, very useful. Right. We'll move on from that. Right. If you are comparing groups, then there's a set of tests to use. And again, you might find it's a little bit hard to believe that the number of people who've come to me with their results, and they don't even know that that's what they're trying to do, is to compare 2 groups. All they know is they've got some columns. No idea of what's to be done. No idea that what we're trying to do is compare the mean of livers with the mean of kidneys and see if there's a difference. Obviously, many students do understand that, but not all. So it's absolutely critical that you know what analysis you want to do. And I'm not even talking about the name of the statistical test. I'm just talking about what you want that test to achieve. For example, comparing 2 groups, as in a student t-test. One-way analysis of variance, comparing more than 2 groups. And one of the things I have learned, you see, is that the knowledge works both ways. When you know a little bit about statistics, in other words, you know what tests could be applied, it becomes easier to look at your data and decide what you want to do with it. When you have no idea what could be done to data, then it's very easy to look at your data and not know how to start. So some basic statistical knowledge really is essential, not so that you can do the stats yourself, not only so that you can guide the statistician, no, that's important, but you will just learn basically by knowing what tools are available to analyze data. It will give you some idea of how and what to analyze. Just making that point. And if your results are non-parametric, Mann-Whitney U-test. So it's like if you've been on my stats course, I have some insight. You look at the graph on the left, you immediately recognize this wants ANOVA. Look at the one on the right. This one wants the Mann-Whitney U-test. The graph just sings it out to you, or the Kruskal-Wallis for more than one. Right. And this is more for the writing up. This is just how we describe it. Right. So, but this, however, is relevant. You do need to know what stats your data require. And as I've just said, if you know your stats, you'll have a better idea of what your data requires. You can't really do the one without the other. Right. Tests of association. If your data is going to look like this, it's called tests of association. 20 males in health science, 40 in law, 5 females in health science, 50 in law. Is that a statistically significant difference? Are females really much more likely to study law than health science? On the face of it, it looks like there are 10 female lawyers for every 1 healthcare practitioner and only 2 male lawyers for every healthcare practitioner. Is it significant? So that's where we're going to use Fisher's exact test. And if there are more than 2 groups, chi-squared test. But again, it's not the test that's important for today's talk. It's just the being comfortable with the situations in which your data can be expressed in tables like this. And if you set it out in a table like this, then it's going to become quite obvious what the comparison is that's required. But so often, as we always saying in these talks, it goes back to being able to state your question, not just your overall research question, but each subsidiary question along the way. This table is the answer to, are females more likely to study law than males? Okay, that's what this table tells us. And that makes it obvious that we need to do some sort of comparison and find if it's significant. And if you ask somebody to look it up, you'll find that chi-squared and Fisher's exact test are just the sort of test for this. But again, making the point, if you don't understand that that's the question you want to ask, and you don't think to set out the data in that sort of table, then it'll probably never even occur to you to do this sort of analysis. And again, if you just go and throw yourself on the mercy of the statistician, well, that's the right word. You are completely at their mercy as to whether they themselves understand that question in your data, coming from a very different background to you. They may not. And then they'll go and analyze average age of males and females in health science or something and tell you that mean age is the same, which is a useless bit of information and has totally thrown away this very interesting bit of information, the heavy skewing of females towards law in this example. So your statistician is not there to interpret your data for you. Okay, they are there to run the stats when you have presented the problem. And this is the format in which this should be presented to them. Right, that would just be writing it up. Then correlation. Okay, something we're talking about in the advanced course at the moment. Whenever you have two axes, two sets of numbers, this is usually the sort of graph that you want to do. This particular individual, for example, scored 30 in biology and scored 32 in science, physical science. And this one scored 48 and 80, or whatever it may be. Whenever you want to compare that sort of thing, in other words, think of drawing a line through the data, then your go-to test is correlation and regression. And this is the sort of thing where you make your data much, much poorer by aggregating all the 10 to 20s, all the 20s to 30s, all the 30s to 40s, because you can't do that sort of analysis on that information. You're throwing away much of the richness by compressing everything into the middle of that block. Right, as we mentioned. Right. Okay, the rest is not quite so important for today. It's again a writing, but it's perhaps we'll just go into a little bit of detail. This is something that confuses a lot of people, and I myself frequently have to go back and consult these references. How exactly do you describe what you did with your data in your paper? Okay. And the bottom line is, the more you state, the better. Reviewers can always say they think you've said a bit too much and you should take it out. But it's increasingly recognized that a major source of scientific error and of fraud is papers that are too briefly written. So somebody reads a paper, sees the results, but does not know that you used the Mann-Whitney test instead of the student's t-test. And had they known that, and known that the student t-test is in fact more sensitive, they might look at your data and say, you know what, I think they would have found significance here if they'd used the right test. They cannot do that if you have not described what you actually did with your results. So gradually the editors are tightening up on such things as not only stating what statistical tests you did, but also stating what data was omitted and why it was omitted. Okay, when you chose to alter certain things and why you did so. In other words, everything has to be defensible. And this partly, unfortunately, because increasingly these nasty cases of scientific fraud are becoming evident and apparent, where people have been willfully doing things to their data. And in fact, it's rapidly approaching the stage now, and has started with some of the best journals, that they will not publish your paper unless you make all your results publicly accessible. In other words, they will not publish your paper until all your spreadsheets are on the internet, so that someone else can go back and rerun all the statistics on your data and say, but hey, they left 5 people out, or why are these dates here from before the date they claimed the study started, and so on, and so on, and so on. Right, so as you analyze, be aware that it's not something you can just do in the dark and people will always just believe and accept what you say. You may very well be called upon to explain and to justify the analysis you did, how you did it, and in particular, the things that lend themselves to changing the outcome, like leaving out some data because you think it's not right, or because it seems to be, out of range, or whatever it is. Right. I think a point I've made this already. You do need to understand the statistics used to analyze your data, even if you can't do the tests yourself. Right. Then the analysis and the results fits in to the whole business of writing the paper, which Colleen is going to go through in June with us in detail. Okay. Introduction, who or what you studied, what you did, how you handled the results, how you analyzed the results. That's all there in the methods. It's not just subjects and methods. Increasingly now, there's the expectation that you'll state how you handled the results, particularly, as I said, when you manipulated the results, you have to be able to justify why, and how you analyze them, right? And then that leads on to results, discussions, and conclusions. Right, I don't think this is appropriate for today, but I did have a little section on reporting p-values. Okay, and we'll save that for the appropriate day. But there are, in fact, rules as to how many significant figures to use, how to report p-values, when to use confidence intervals, and so on. But I think we'll save that for a writing afternoon. Right, so we finished a little bit early. Colleen, let's hope there'll be some discussion.
Yes, I'm going to open the floor to anybody who wants to ask a question. Just unmute and ask. And just to reiterate, the whole of June, we are going to be looking at writing a paper. So we'll go into details in the afternoon where we're going to be talking about reporting results. We'll get Prof. Heft to go into details about how to present your p-value, etc. on that particular day. So June is going to be what is called worldwide an ACRIMO, which is an acronym for Academic Writing Month. And we are going to have sessions on a Wednesday and then evening sessions on Thursdays and Mondays, where we will write in groups. And hopefully by the end of June, we'll all have a paper. Those of you are obviously ready with data to write the paper. And also to mention, next week, I'm going to be stepping right back and doing the very basic statistics, going through what is a numerical variable, what is a categorical variable, what do we do with them. So I'm going to be giving a kind of grade 10 version of the statistics. So if you get your head around that, then the beginner's course that Professor Heft offers will make a lot more sense. It's also just enough for you to do your own descriptive statistics and take them along to your statistician, and also enough to make your statistician realize that you're not totally green, that you do understand that certain tests go with certain types of variables. So we'll be doing that next week, and then looking at writing for the whole of June. So let's open the floor. Anybody got anything to share with us about any aha moments that you've had with your data analysis, where you've realized something that you didn't anticipate? Okay, there's a question there. How do you determine significance in terms of study sample number? Richard, do you want to take that one on?
Yes, and hello, Anati. Bottom line, we can't answer that in a sentence this afternoon. It does require an hour or two to actually explain and give examples. And I'll actually be doing that, I think it's Monday next week. It's the 4th day of my intermediate statistics course. So perhaps people would like to join up for that. You know, the details are on the our website, or else if Unati and other such people were to approach me, I'd be happy just to put on a once-off on sample size. It's something I know that troubles everybody.
There was also a question about qualitative data. I think we'll be running qualitative workshops in the 2nd semester. We've got some plans for the 2nd semester as well. But qualitative research is very different from quantitative, and how you analyze your data is often very project specific. There are a couple of known methods like thematic analysis, which is used mostly in clinical sciences, but there are other ways of analyzing the data too, using different kinds of software packages to help you. What I'm experiencing at the moment as I'm going through examiners' reports is just about every sentence can be a data point. So it ends up qualitative data analysis takes a lot of minds on time, whereas quantitative data analysis, once you understand what your numbers are going to do, is relatively fast. Musa, you've got your hand up. Would you like to just unmute and ask your question?
Thanks for that. I would really love to be part of that qualitative presentation because I do a lot of that now. But my question around today's presentation, you see, sometimes you deal with the students, and even before you look at the data, and they just ask you in general, what is important to do when you look at the data? So what I want to just say now is I need some correction in terms of what I'll say, and then you can say, no, in general, this is what you're missing. So I think first you describe the data. You always will have to describe the data in general. No discrimination. And then secondly, you look for relationships in the what's the other analysis? Non-descriptive, what do you call them? Inferential statistics, where you look for relationships and so forth. I know there's one more level to that, but in general, what would you say is something you can say just in theory? These are the 3 steps that you want to do when working with quantitative data. Obviously, each study will have its own unique points, but what are the 2 or 3 things that one needs to look out for and say, okay, as my student, these are the 3 or 4 things that I want you to go and look at, just in general, and something that applies to almost every quantitative study. Sorry, I went a long way around. I hope, yeah.
Unfortunately, it was breaking up quite badly my side. I think somebody's going to have to restate the question for me. I didn't actually catch all the key words.
Okay. Okay, Musa, just go back to your 3 points that you're wanting Prof. Heft to elaborate on.
Okay, what are the key steps that are general across all quantitative data analysis? So that's what I'm looking for. If you're working with students, what are the key steps of quantitative analysis?
Okay, I guess the first thing would be just your descriptive statistics. That is summarizing things in terms of means and standard deviations, numbers, totals, subtotals, things like that before you get onto any actually fancy statistical analysis. And that is what I suggested is best actually put out in tables and represented with graphs. That's usually the starting point. From there, as in, for example, here you've got the mean and standard deviation for the males and one for the females. And there you've got a graph showing that the males are higher than the females. Look at that, think about that, and that will suggest the next step, which is to do a statistical comparison of the two. So in some ways, I guess it's a bit like building a house. You know, you put down the first few bricks, and then that suggests the next few bricks to put on top of that. And eventually you keep on adding and adding, and by the end of the day, the house is actually built. It's not usually the case with complex results that you set out on the first day, and by the end of the day, you finished your analysis. You get new ideas as to what you should be doing with your data as the initial results of analysis come in. So to me, that's the first step, is just summarizing everything in terms of means, standard deviations, ranges, numbers in boxes like the male, female, law, health science, or whatever it may be. In other words, it actually goes back to what I said earlier, understanding your data, understanding, you know, what they are able to tell you. And then we take it from there.
I would also go a little further back, and if you're talking about what you're going, advice for students is right from scratch, make sure that you are collecting variable data that is directly related to the research question. I think that is the first step, and Prof. has given talks on that earlier, to make sure that they are collecting the correct data in order to, one, describe the sample, and two, to answer the research questions. The next thing I would add to that is, I've got a rule that collect the data in numerical data if possible. Do not start categorizing early on, because categories can be created later, but if you collect in categories, you can't go in numerical later. So I would say that's another rule that I would give to students. And then I would add one that just get your basics down. And Prof. Heft had some slides that are very useful, and I will go into more detail on them next week on what is your, how would you have your comparisons, what data would you compare, what are you going to look at in test of association, etc. Just to know that they're different packages, and it's not a lot to learn it. If you know the flavors in a packet of licorice, all sorts, you're going to be able to get your head around the basics of the different types of tests for different types of research questions. So I would say that those are the important things. Richard, do you want to add anything to that?
Not really. I think that's entirely true.
One bit I missed. Must you always have a deviation analysis if you had an association analysis all the time? Or it's just driven by the direction of your study?
Sorry, I think I'll have to ask you to repeat that too. It was breaking up.
Okay, let me try again. If you have some analysis of an association, does that automatically mean you must have some analysis of deviation, or that's driven by the direction of your study or your study interest?
Sorry, I have to ask, what do you mean by an analysis of deviation? I think maybe this is too technical a question for today.
You had some variables that you were looking at, and you thought,
okay, are you asking about whether it's normal or skewed?
Well, I think one step beyond the normative kind of analysis where you look at your normal curves and all of that. But I'm talking about the inferentials. If you had any associations that you want to analyze maybe between one variable and the other, must they be accompanied by deviations as well? So what I'm saying is, if you analyzed any correlation kind of a relationship, must you also analyze a relationship that looks at the opposite? In other words, to prove that since the one thing exists, the other doesn't exist, or it exists in an opposite direction. I hope that's clear. I'm struggling with my words here.
Right, yeah, I don't think I can answer that generically. It sounds like a very specific issue, relevant to your particular work. So perhaps you and I, you should get hold of me at some stage, and you and I can have a private chat about that when you've actually got your data in front of you.
Okay, thank you so much. Thanks.
Okay. Yes.
Are there any other questions, any other comments? I'd like, there are some very experienced researchers in the audience today. Have you got anything to share about a moment when the data started speaking to you? And I would like to go back to what Richard said. If you start off with your descriptive data, at that point, the data starts to talk to you. You start to see things that create new questions in your mind for later analysis to take to your statistician, or even for you to work out on your own. So starting with your descriptive statistics is a really good way to get your head into the data and get the data to start speaking to you. I remember my PhD supervisor, I invited him to lunch one day. We had a big family lunch and he was sitting there. And I had in that week, for the first time, had an aha moment where I had the experience of data talking to me. And I mentioned that. And he raised his glass and said, "This is a beautiful moment for a lecturer." And I always remember that, because when I see it happening, I see it as a beautiful moment as well. So how many other people have had experiences with data where you have thought you've had a beautiful moment?
I certainly have.
Yeah. You want to be specific, but we've still got 5 minutes, and I think a lot of people are racking their brains still to try and think of them. Do you like to share some more on that, Richard?
It's something that happens numerous times with an interesting project. So I can't think of specifics at the moment. I just know that it happens, and not infrequently.
Yeah.
And often it emerges in discussion. Like I've mentioned this Dr. Mayuri Govind, the radiologist, and I have learned so much from her, and vice versa. As we argue what the result, and I don't mean argue in an unpleasant way, what the results mean and discuss, then these insights come, and we sit and we run that particular analysis straight away, and to our amazement, a curve comes out or a straight line comes out, and it's followed by an aha moment because it has a meaning. Good heavens, look at that. Who would have thought that we would find that experience correlates with score or whatever it may be? So that's most of the fun in science, I think, when you think about it, is actually during the analysis. This is when the rewards of your project emerge. As you analyze things, your project starts to give you presence, the excitement, the things you hope to prove, the things you never knew that you were actually going to find or prove start emerging. After that starts the drudgery of actually writing, but even that has got a pleasure of its own in a way.
Hi, Richard Yunus here. May I ask a question?
You should be one of those sharing your research experience with us.
No, Richard, the one thing that I've noticed is that when you got a hypothesis-driven question that is being answered by research, and let's assume that question is not quite addressed at the end of the research, and you make some other observations that are interesting, it looks like the scientific world frowns on the analysis proving something that you were not originally set out to prove. And I was wondering if that's your sense as well, and why is that skepticism around that? Am I making some sense to you?
Yeah, no, absolutely. It's something I've often had to think about. The way I see it more now, I think it's a legend that gets handed down from person to person to person, that it's frowned upon, you know, to come up with results other than those you set out, because it's never actually happened to me. I've never yet had a reviewer or an examiner criticize work that we or a student has done for that. And to me, it would also be very short-sighted, because I believe that's how science progresses, and particularly the somewhat less exact sciences like our clinical sciences, you know, where things don't proceed neatly and according to plan like they do with test tubes. And we often end up making very interesting observations that weren't made before. So my personal belief is, what I tell my students, for example, in their PhDs, is that they must state their current objectives as they turned out as the work unfolded, but then they must provide an explanation of how these differed from the objectives they set out and why they've changed along the way. And I've always found, you know, examiners seem to be very, very happy with that. I feel it's otherwise, it's inviting examiners to say, but you haven't answered your objectives, what's going on here? So my belief is that you can do most things in science as long as you explain fully and justify, you know, what it is and why you've done it. And certainly when you think about it, I'm sure both, you know, you and I have actually read plenty of papers in which people expressed surprise as something interesting they found and then state how they went to follow up on that. So no, I think it's generally seen as a strength. But again, there is this legend that's passed on from student to student to student that you've got to stick to your objectives. I don't know, Colleen, if you have any thoughts on that.
I believe that objectives change as research progresses. That's science. The one big issue that must be borne in mind is that you are still working within your ethics. And if you're not, then send an ethics amendment in. They're not onerous to do. And really, it's as you get into your research that you start seeing the next step, and a quick aside is going to add quality to the PhD, for example. There's an example I had this morning where I've got a student who's now working at the MRC, and she's got a 3-month wait before she gets some of the data back. And somebody at the SAMRC has said to me, well, why don't we give her some primers, let her learn some pyrosequencing, and come up with a set of data that we can compare to the NGS data. We're still covered for ethics. It's still just looking at methylation of particular genes. Ethics are covered, but now we've got an opportunity to increase the skill level of the student and also possibly get another publication. So I do believe that as long as you're sticking to your ethics, science moves. It's organic, and I've got no problem with that. Does anybody want to comment on that?
Yeah, actually, Adremi made a good point in the chat, if you can see that. That's what I was actually referring to, is often people would accuse you of going fishing on a fishing expedition, looking for something that would kind of make sense and has statistical significance, and then you are redirecting the focus of your study onto that particular question because it suits your outcomes.
Are you doing good science? Are you pushing science forward? I believe that it's all about science. It's not about looking at what you decided in 2021 as opposed to what you can do in 2022. So.
Thanks, Colleen.
But I've tried to answer that too, Eunice. It's a very good point, Adaremi, partly covered in that you must adequately explain why you've sort of changed tack and doing something else. But also it's got to be a good, valid conclusion. I think it's usually fairly obvious when somebody has dredged and come up with some minor little point that was slightly significant. It just looks forced. Okay. But if it is a really interesting insight, I think, and you state it as such, and it makes scientific sense, that's the point. Then, well, it would be completely wrong to suppress it. Colleen will tell you too, you know, I'm not making the best use of your science is poor ethics.
Yeah.
If it's scientifically plausible and it's sensible, then I think it makes sense to state it and support it.
Yes.
And if it's rubbish, if you are just extending things, just sucking things out of your thumb, it's not going to get published anyway. And that's why I really like the PhD by publication, because these kinds of things will be ironed out in the process. Adarimi, you've got your hand up.
Thank you very much for addressing my question. So at what point must one now declare this to be able to make it acceptable? So say you found something that wasn't planned, at what point must one then declare it?
I think right up front, at the point at which you've found it. And if you think it's worthy of publication or including in your research, if it's pushing science forward, if it's going to be a step to getting the knowledge base of your area extended, I think you do it right up front.
I don't think we just make too much of it. Those things are often just preceded by, in the discussion, for example, by a common English phrase like "an unexpected finding was," or "contrary to our expectations, we showed that." It's often just introduced, the standard English phrase to express a change of expectation, a change of plan. I don't think we must build it up into too much.
So in other words, it doesn't necessitate a change of your protocol or anything like that.
Well, I think Colleen mentioned that if it's a complete change of your protocol, well, yes, then you're going to have to revise ethics if necessary. And most definitely when you submit a thesis, it must have a complete reflection of how the protocol changed. Bottom line, as I said, if things are put out there publicly, upfront, honestly and openly, nobody can criticize you. It's only when things have happened that have not been disclosed to the examiners and reviewers that they are likely to be upset.
And just to clarify, if you are using the exact same data that you've got ethics covered for, but you're able to see a new research question in that, and you're not going out to find extra data, then you don't need to go back to ethics. It's just that if you're wanting to add something find another one more variable, then you must go back to ethics and add that to your data set. But using your data set to its maximum potential to increase knowledge is not a negative thing. It's not data dredging as a negative thing, but the 4 points that Prof. Hef put out, the massaging the data, the selection of particular data sets within your data, just neglecting to mention some of the data, that is unethical. But not using the data that you've got to its maximum potential for pushing knowledge forward. Okay, I think we have gone past our 1 hour, unless there are any other burning questions. I'm going to thank everybody for attending this week and just remind you that next week we're going to look at the very basics of statistics again. It's for those people who've got absolutely no clue, who are just starting out again, who want to get their heads around what do we do with a categorical variable, a numerical variable, what is skewness, why is that important, etc. So we'll see you all back same time, same place next week. Thank you very much for attending, and thanks Richard again for your very informative talk. Bye-bye everybody.
Thanks, bye-bye.
Thank you all, thank you.